Hey, good afternoon. So I didn't see any new homework questions on Piazza, so if you have a question, just put it on. So today we're going to be talking about binary trees. A binary tree is conceptually simple. It's a tree where every node has two children, or maybe once in a while you might have one child. Or of course for the leaves you would have 0 children. So generally you expect 2 children. And here we have a leaf. So of course a leaf has no children. And you might have once in a while have a node that has 1 child. So it simplifies things when you know that you have at most 2. There's one minor difference between a binary tree and an n-ary tree that you need to pay attention to, and that is if you have an n-ary tree where you can have any number of leaves, there's no particular order or direction to them. Whereas with a binary tree there is. So when we have a tree like this, we're going to consider it to be different than the same tree where the node goes to the right. So in a binary tree, the left and right are marked. Whereas in an n-ary tree, if you have a tree with one node, there's no notion of left or right. So in all situations that you actually encounter in practice, that's going to be totally clear from the context. We're going to be going through a few examples of binary trees today, because they do occur all over the place in computer science. We're going to be looking at decision trees. We're going to be looking at Huffman trees for encoding of next time. We're going to be looking at binary trees the lecture after that. Binary search trees. Binary search trees are a way of implementing sets efficiently. And we're going to be looking at expression trees a bit. So just so that you can see that these are really ubiquitous data structures in computer science. So I will start with those decision trees. And by now you've all seen them in that homework assignment. So it's a very simple kind of thing. In every node except in the leaves, you have a question. And that question has 2 answers, yes or no. Hence it's a binary tree. And in the leaves, then you have an answer that says after having done all of these decisions, that's what the answer is. So here's this example where it's an animal guessing thing. So the first question is it a mammal? And does it have stripes? And if you say no, then the only mammal that has no stripes that this particular data set knows about is a pig. Of course, there are others. And so if it wasn't a pig, then one would have to grow the decision tree. And that's exactly the point of the first homework assignment. So in the first homework assignment, you first of all need to program the dialogue with the user. And that dialogue is pretty easy to implement. You need to have a reference to the current node. So you start at the top. So that's your current node. And then whatever data item is stored in that node, you just ask the user. And then you collect the user's answer. The user's either going to say yes or no. If the user says yes, then you follow the link to the left. If the user says no, you follow the link to the right. And that's your loop. You keep doing that. When you stop this process when you get to something that's a leaf. How can you tell whether a node is a leaf? And you tell by the green color and the fragrance. Yes. Yeah, if it has no children, it's a leaf. So, actually, is there a situation here where could you have a node with 1 child in this particular tree? No, it doesn't look like it, right? You either have 2 because you have a question with a yes or no answer, or you have 0. It doesn't really make sense to have a question with only one answer. So this particular kind of tree has that property that you have no nodes with a single child. Other kinds of binary trees do have those nodes, and so you have to be prepared for it in other programs. Here we don't have to worry. All right, so if it's a leaf, in that case, you simply tell the user, hey, it must be an ostrich, or whatever it is that the leaf said. And our program then says, well, what if it wasn't? So we'll ask the user, and if the user says, no, it wasn't, then we say, can you tell me some fact that is true about an ostrich but false about the thing that you were thinking about? And, or the other way around, I don't remember. And in that case, what the transformation that you then have to program is you then have to add the new question here. You have the new answer, and then you have to reroute that one to point here, and this one to point here. Right? That way the tree grows to next time be able to answer the question. Now, actually, of course, what really needs to be true is that that question also keeps track of the entire context. I did that at one point. I did this wrong in my answers. So the question needs to be able to tell an ostrich apart from the new creature, knowing that all the other things are also true. So if someone were to now say it's a dinosaur, well, a dinosaur doesn't fly. If someone now says it's a swallow, then that couldn't be true, right? Because then we should have never been here in the first place. All right, so so from an implementation point of view, it's not difficult to implement. You have done much harder rerouting of nodes in the previous assignment. So here you need to create a new node and just link it up in this particular way. Someone asked, what if I leave the program? It won't remember, and that's sadly true. Right, this program here, it'll only remember in the current execution what it learned. It has no way of writing out its tree to a file. That's a nice enhancement, and it's a part of some other exercise that I just didn't assign because I felt it was getting us kind of far afield from what we wanted to cover. So it is, of course, possible to write a tree out to a file and then to read it back in. And it's maybe not pleasant, but it's certainly doable. And if we had infinite time, that would be a great assignment. All right, so those are decision trees. Conceptually, it's easy, I think, and it's mostly there to get you used to this concept: binary tree, left and right child, that kind of stuff. Now we're going to come to this notion of balanced trees. So in a balanced tree, the length of all the paths from the root to one of the leaves is about the same. In general, it can't be completely the same, because if the tree is not completely filled out up to a particular level, like this one here is missing a few nodes here or there, just because it just doesn't have enough stuff in it, you can't expect the length to be 100% the same. But if they're pretty much the same, within one or two of each other, then we'll say the tree is balanced. And if, on the other hand, it looks like the one on the right here, where some of the paths, like this one, are dramatically shorter than others, then we'll say it's unbalanced. And why do we care? Because there are many algorithms that work on trees that need to look at all of the elements along these paths. And so when you put n elements in a tree, and when the tree is balanced, then you can often write an algorithm that says, look at the tree on the left, look at the tree on the right, do some work with them, and those algorithms tend to be fast. Whereas if one has to go through the entire, like a long chain like that, then it turns to be essentially like a linked list, which will be slower. We'll see that very dramatically in 2 lectures when we look at binary search trees. So the criterion for a balanced tree, it's a little squishy. It says all of those lengths from the paths from a root to any of the leaves should be approximately the same. And there was an unfortunate question on the quiz where the person who authored that question wanted to get at that concept and muddle it up with the height. And that didn't really work so well, because the height is, that's the length of the longest path, And we're not really interested in the length of the longest path here. We're interested in the average length of all paths. And so if all of the paths are within a reasonable bound of that average, then we call the tree to be balanced. All right. Just a bit of tree arithmetic here. If I have a tree of height h, I don't know what is the smallest number of leaves that this tree can have. Put it on Piazza. Paul. Okay. Okay, well, I'm glad that the majority has had the right answer. So, of course, if you have H leaves, and they are, no, sorry, H nodes, and they all lined up like this, then you have exactly one leaf. And that's the smallest number of leaves you can have, right? You can't have no leaves for a finite tree. So, so that was, in fact, the correct answer. And so a surprisingly large number of people said the smallest number of leaves was 2 to the h minus 1. And so that's, of course, the largest number of leaves. And there's actually a useful lesson in there. If you want to have a substantial part of the audience not understand a particular word that you're saying, say it louder than the others. And then they'll think the exact opposite for some reason. So this trivia fact may come in handy sometime. So the largest part is it. So let's say the question was asked more sensibly. Would the largest one be 2 to the h minus 1 or 2 to the h minus 1? So let's just quickly see how we would settle that question if, in fact, we were asked for the larger one. Let's say that was the question before us. So you would presumably get the largest number of leaves, when like everything is nicely filled up. So if you look at a tree, so let's look at a tree that looks like this. What's the height? So the height is the length of the longest path. They're all the same length. This path has length 3 because we count the nodes. So this is height 3. And okay, how many leaves does it have? It has 4 leaves. That is 2 to the 3 minus 1. Right, 2 to the 2. So that means that this one would have been the right answer if I had asked for the largest. What is this number? That's the largest number of nodes that it could have. Leaves or inferior nodes. Right, in our example, that would be 2 to the 3 minus 1, which is 7. And so this thing has 7 nodes. So if your height is h, you can have up to 2 to the h minus 1 nodes. All right. So let's look at the implementation of a binary tree, and that'll work for a binary search tree that we'll see soon enough, or for one of those decision trees, for any kind of binary tree that you might want to implement. We have a root node, and then the node is one of these nested classes here. And then each node has a node to the left and a node to the right. So whereas for a general tree you just have a list of nodes, here which gives you the ability to store an arbitrary number of them, here you have exactly 2, one to the left, one to the right. And of course each node can also carry some data item here. All right. So if you want to write any function on one of those binary trees, actually let me just make sure that you understand this protocol here with this question. Similar to one that we had last time for general trees. So here I'm constructing a binary tree, and I want you to construct it sketch it out on a scrap of paper and tell me what it looks like. Since I can't ask you what it looks like, I'll just ask you what the leaves are. So let's see. So Fred is going to be accessible from the root. Then Fred has as its left child Barney, which itself has children null and null, and as its right child Dinah, whose left child is Wilma, and I'm not going to draw the nulls again, and whose right child is also null. So this is what the tree looks like, and so ignoring the nulls here, we then see that the leaves are Wilma and Barney. That's answer 3. So let's see how we're doing. And just about everyone got this. All right, so this is easy. Good. So notice this very compact form of building the tree where I just keep calling the constructor. The constructor returns a tree, and then it also gets trees in its various levels here. So each of those expressions is a tree, and I stick all of these here together in this recursive way. And so I don't have to actually set up variables for each of one of those subtrees if I don't want. All right. Now, as with general trees, most computations that you do on a tree, you do recursively on the subtrees. So let's look at how you would compute the height. You would say, well, I'm going to compute the height on the left. I'm going to compute the height on the right. I'm going to take the max of the two, because I want the taller of them. And then I add 1 to reflect the current level. So generally, I find it helpful to sketch out one of these little drawings where you can then pretty immediately read up what the recursive algorithm is. Then, when you implement it, then you have all of this stuff that and I made the same mistake as last time. I forgot to fix this one here. This one needs to be in the node class here. Whatever, class node. I'm just going to write it on here. Come on. And I'll fix the slide later. So you have a method in the tree class that asks about that method in the node class. So here we're having the first one, here we're having the second one, and I should have moved into the node class. And then I'm asking a question, is it going to work? All right, let's set this up. All right, so just about everyone says there's nothing wrong with it. Let's see. We'll come to the static stuff. Okay, well, let's do it. So the private height method should have been static. I want to talk about that in a minute. The public height method should have been static. Surely not, because that's the one that you call when you have a particular tree and you want to know what is its height. Are the return values off by 1? Well, let's look at a tree with a single element. It has height 1, and let's see what would be computed for it. So it's not null, but it has 2 children that are null. So here we get the 1, and then each of these ones here, this is the height of null, this is the height of null, and each of these is 0. So it does seem to compute the correct value, and so it can't be true that they're all off by 1. And so the remaining question is, why doesn't it have to be static? And there was some confusion about that on Piazza, and so let me explain what this deal is with static versus non-static methods, and then there's another twist that I'll come to. So if we make a picture of what an object of class tree looks like, it looks like this, right? And it has a reference to something in here. That's what an object of class tree looks like. Binary tree, I should say. Now, so in our class binary tree, now we have some methods. The first method that I had was that public height method. And it said return height of root. Now, how do I know that this method cannot be static? It can't be static because it references an instance variable, namely root. And so when one calls the method, one has to know which root. Each tree object has a different root, and to know which one, there has to be some way of knowing what tree are we talking about. So when you have a regular old method, a non-static method, it has an implicit parameter which is called this. And this is set to the particular tree that one is talking about. And then the root here means this dot root. So a regular method gets this reference as a hidden or implicit parameter that tells it what object we're talking about, and then when you reference any instance variables or any instance methods, they get invoked on this. A static method is simply a method that has no this. So you can always declare a method as static if you have no need to look at this, if you never refer to any instance variables in that method. So let's look at this particular method here. And what we should check, it's a method of the node class, right? I forgot to put that in here. It's a method of the node class. And so the question is, does it ever reference an instance variable of node that's not qualified? So if you look at a node object, it looks like the following. A node has a data field, it has a left field, and it has a right field. So let's see. Does this method here reference the data field? No. Does it reference the left and the right field? Well, it does. So why do I say I could make it static? Because it doesn't refer left and right of itself. It refers left and right of n. So it's a subtle point. It references the left and right field of some other node that is being passed in over here. So therefore, because it doesn't reference an unqualified field, therefore it can be static. Like over here, contrast that with root. It doesn't say something dot root. It just said root. So this method here didn't need this because there's nowhere in here that we're referencing a field without qualifying it by saying with which object we want it. So it can be static. What if I omit the static? There's no harm done. All it means is that this method gets another parameter, namely the node that calls it, even though it has no interest in looking at it. But there's absolutely no harm done with omitting the word static. So you might say, can't I always omit static? If there's no harm done, I just get an extra parameter. And that's almost correct, except there's the other flip side, that if you have a static method, and in that method you want to just call another method without calling on a particular object, that method must also be static. So if there wasn't a primordial static method in the first place, you wouldn't actually ever have to worry about static methods. You'd just get some extra parameter that you could ignore or not. What is that primordial static method? Main. Some idiot, some blistering idiot, when Java was first designed, said, let's make it kind of look like C, and let's give the static main method. If that person had thought for an extra microsecond and said, we're doing an object-oriented language here, and not a dialect of C, and had omitted the main method, you and I would never have had to learn about static methods. The way that the world would have looked is, if you would have wanted to create a program, you would have had to somehow tell the program launcher, make me an object of this class, and the constructor of that object would have kicked off the computation. There would have been no need for main. So anytime that you see a programming language that has a main method, you know it has been either designed by idiots or for idiots. In Java, I would like to think it was the latter. So someone wanted to make Java feel, more approachable, easier to understand for those people who had the misfortune of having used C or C++ before. And that's actually sad because the static stuff is confusing. People have an imperfect understanding of what it means, and it takes a while of practice to get to that. And so I'm going to add to that confusion now with another thing that you're probably going to be seeing on the homework, and that is static classes. So I apologize for not having had a slide for that. So when you have a tree class, and maybe just make it a binary tree for now, and inside that you have a class node node to the left, node to the right, and an object data. Then it's possible to declare this class as well as static. And I want to briefly explain what it means to put the word static here or not to put it here. So when you put the word static, then a node contains exactly those three fields that you see here. Just like a method that's declared as static contains exactly the parameters that you see. If you omit the word static, then there is a secret field that you don't see. So let's omit it. In that case, there is a secret field pointing to the object, in this case the binary tree, that created this node. And you don't see it, but it enables you to reference it. So if you omit the word static, then you can reference the root from inside any of the nodes. Now, I don't think we're actually ever going to have to do that, but we did have to do that in the previous chapter with the linked lists. If you look very carefully at the linked list code, you will notice that, like the iterator, which is a non-static inner class, will once in a while access the head and tail fields of the list in which it is contained. I didn't say a word about that at the time because I was hoping no one would notice. But if you carefully look at it, that's the way it is. And so the same thing is true for nodes. They're actually allowed to make that access. Now, one of the assignments, I felt compelled to give you a... Did I give you a static node class in one of the assignments? Did any of you notice this? Or maybe it'll be in the next one. One of them you're going to be seeing a static node class, and I was in the same bind. It was called from some static method, and in a static method, you cannot access a non-static node class. So when you see that, that's the reason for it. Once we get into that, I'll explain it one more time. It's not the most important thing in the world, but it is. Most people find this entire thing quite confusing. All right. Okay, let's see. Do I want to do this? Yeah, hey. Sure. Okay, one more. Okay, so here. Ah! It hates me today. We got 16 answers, 18 answers. All right, let's see. The public height method should have been static. No. And we know that. Because it's accessing an instance field of the tree. Method returns the wrong value for every tree. The wrong value for every non-empty tree. Well, let's try the empty tree. Empty tree has root no. And for that, it returns the height 0. Does an empty tree have height 0? Well, what about it? Like this tree is not empty. It has only a single root. What height does it have? 1. So because we count the nodes, right? So the empty tree, which has nothing in it, I don't even know how to draw it. Okay, here I have drawn it. It has height 0. Right. And so it seems to return the right one for that. Now, otherwise, though, and this is just such a common mistake that I wanted to show it off again, is here we're computing the height of the left, the height of the right, we're taking the max. Well, if the only number that I ever created was 0 at the leaves, because the leaves give the actual results, and then I take the max of a bunch of zeros, it's always going to be 0, right? So I forgot to put the 1 plus in here. And let's see. What? Oh yeah, okay. So it returns the value, yeah, for every non-empty. Okay, yes. Okay, so everyone, most people got the answer here. So there's just a single tree for which this thing produces the right answer. All right. That's all. That's all I got. Okay, so there's one more thing I want to talk about. Let's see, do we have homework questions? Okay, I'm going to give you one homework hint, though, that I think may be useful. So that's this thing with those plus, plus, minus, the sideways tree thing. Oops, sorry. Plus. Do we have 2 minuses? We have to settle on 2 minuses, right? And so the thing that makes these trees tricky is what happens here at the end. That you have this line of vertical bars going down, except that line peters out, no pun intended, at the very end. And so when this fellow here has to draw its children, he needs to know that before those children there should be 3 blank spaces, whereas when Barney wants to draw its children, it needs to know that before that it needs to draw the horizontal bar. And I mean, this is a famous assignment. I remember when I was an undergraduate student, when none of you was born, and I had to do this very same assignment, and I found it distasteful, and I was very tempted to say the heck with it and put everything into a 2-dimensional array, and then later read of characters, and then later read out the characters. And to the degree that the lab assistant at the time it made an amendment to the assignment saying that would be dishonest and was not allowed. So the intent is you should really do this a line at a time. So, and the key observation is this, and that's, I think, where people get it wrong. The key observation is that it has to be the parent who knows and who can tell its children whether or not to draw the bars or the spaces. So the parents know best, unlike in real life. So the parent tells Barney, say, you need to use the vertical bar for all of your children. And it tells Peter, you need to use the space for all of your children. So in fact, the parent tells all but the youngest child to use the vertical bar. Now notice that the parent might have grandparents, so it might have been told by its parents to use whatever as its prefix, so it needs to concatenate its own prefix to what was handed to it by the ancestors. And the other confusing thing is that now Barney is told to use the vertical bar, and that's in fact true. For Barney's children, it needs to prefix them with the vertical bar. And now Barney must do one other thing. It must ignore that advice for itself. So for itself only, Barney gets to draw the plus and the two minuses instead of what the parent said. So it has to follow what the grandparent said and then put the plus minus minus there. But for all of its children, then the advice from the parents is sound. So this is actually good, right? You get to listen to your parents, or rather you tell your children to listen to your parents, but you ignore it and replace it with your own superior knowledge. So that's because every node itself is prefixed by the plus, minus, minus. That's it. Once you implement that, it's a very easy recursive solution. There's one other twist, unfortunately, and that is that the root is a little different than everything else because the root has no prefix. So those are the two pieces where you need to watch out, that the root is different and that every node itself ignores the last three characters from the parent's advice. When it takes the grandparent stuff, replaces the last ones with a plus, minus, minus, and there you go. All right. In terms of the lab, I put on lab 8 here, but I was a little optimistic. So we will go on with lab 7, and I will have a bit of a summary at the end. And I added one other problem to it, so those of you who blazed through this thing get something to do. And that was actually kind of an annoying thing. Those of you who stayed till the end last time noticed me starting up some grand discussion with this picture. Where I said, okay, now we partition. Here's from, here's P, and here is Ch. And then we process the left and we process the right. And recursively, since each of them is smaller than the whole thing, it has to come to an end. And then at that time, I hesitated and said, gosh, what if one of them isn't smaller than the other? What if the partitioning is like this? What if it happens to be that all of the elements to the left are less equal to pivot, and none of them is greater than the pivot? That would be bad. I didn't say that at the time, I just left. What would happen in that case? So let's say that partition on a particular array had this effect. That partition would give me back two subarrays, one of them containing the entire first array, and the other one being empty. What do I do with those partitions? I apply my algorithm again, whatever it was, sorting, finding the median. What is the very first step in that algorithm? So normally, let's look in the happy day situation here. So I have my array on the left. And so I recursively process the array on the left. What is the very first thing I do? Well, what is the very first thing I did with the big array? Well, I couldn't get sorted. I partitioned it. Right? So what I now would have to do is I would partition this guy again. All right, well, let's apply it in the unhappy situation. So here's my first one here. What would happen when I partition it? Well, presumably I would get it right back together with an empty one. And I would recursively apply my algorithm to the one on the left. The very first step of that is to partition it. Well, in this case, I would get it right back. What would happen? What would happen? Would time stand still? Would all motion of the universe cease until this has been resolved? Maybe not of the universe, but certainly of my program, right? It would keep calling itself and itself, and eventually it would die with a stack overflow. So that would be bad. And so I was really worried about this. This is in a printed book that's been gone through 6 editions. Right, not for the median stuff, but for sorting. I mean, the quick sort thing has been there all this time. And so I was relieved to find out by having a very, very close look at this particular algorithm that it can't happen. And so I do want you, if you at all have that time, to go through that. So that's my part G that I added on. And kind of the reason that motivated me to add this as an extra exercise, even though it has nothing to do with programming, is that we're right at this point, and people often ask me, I've been programming for 6 years. Why can't I go straight to the master's program? And then I have to kind of explain the difference between programming and computer science. And this kind of really gets at the difference very nicely, because here we're not interested in how does this look like in Java or in C++ or in Python or something, but we're interested in what is this computation doing? How can I know that this algorithm, just independent of any particular implementation, how can I know that this algorithm will actually succeed? All right. So let's get going with that. I think there should be enough stuff to keep everyone busy until the end, and then I will talk a little bit about it before we're putting this lab to rest.